Okay, welcome back. If you're doing any kind of data analysis in Python, well, you're basically living in the Pandas library, right?
Absolutely unavoidable.
But before you can really wrestle with those big, complex data sets, those multi-column data frames, you really have to nail the fundamental piece.
hmm
So today we are doing a deep dive, getting right down to the bedrock of Python data science, the Panda series.
Yeah, and this is super important because honestly, if you get your head around this series, the rest of Pandas starts to make a lot more sense. It's the basic building block.
The atom, you could say.
Exactly. It's the atom that makes up the molecule of the data frame. Grasp the series, and data manipulation in Python just clicks. It really does.
All right, let's unpack that core definition first. What is a Panda series, fundamentally?
Okay, so the sources are pretty clear. It's a one-dimensional labeled array.
One dimension, labeled array. Okay, so like a single list of things.
Sort of, yeah. Think of it as just one sequence of data points. The best analogy, especially if you're coming from spreadsheets or databases,
Yeah.
is really just like a single column in Excel or one column in a SQL table.
Mm.
Simple, linear, but, and this is key, way more flexible than just a list.
Okay, flexible. You mentioned it's a powerful container. What does that mean in terms of what it can hold? Beta types.
Yeah, so it stores heterogeneous data types. That's actually a huge plus.
Wait, hang on. Heterogeneous. So you could have like names, which are strings, and ages, integers, maybe even some dates, all in the same series, the same column.
That's exactly it, which is, pretty different if you're used to stricter systems where a column has to be all numbers or all text.
Right, that is different.
The series handles integers, floating point numbers, strings, Python objects, pretty much anything.
Mhm.
But the real magic, what really sets it apart from a plain Python list,
What's that?
it's the indexing. It has this dual capability. You can access data using integer positions, 0, 1, 2, just like a list, or you can use custom labels.
Ah, okay. So position and label. That sounds powerful.
That duality is the secret sauce. It really is.
Fascinating. Okay, so let's get practical. How do we actually create one of these single column powerhouses? Let's talk creation and understanding that index.
Well, the good news is it's super flexible to create. You can build a series from lots of common Python things you already have,
Like what?
like a standard Python list, or a NumPy array if you're doing more numerical stuff, or even a Python dictionary. You can even make one from just a single value, a scalar.
So it plays nice with existing structures. That's good.
Yeah, it's crucial because data comes in all sorts of messy forms, right?
True. So if I just make a simple one, say from a list of 4 numbers, like 10, 20, 30, 40, what do I actually see when I print it out?
Okay, so the output immediately shows you that dual nature we talked about. On the right-hand side, you'll see your data, 10, 20, 30, 40.
Right.
But on the left, critically, you see the index. And if you didn't specify one, Pandas just gives you a default integer index. Starts at 0, so you'll see 0, 1, 2, 3 next to your numbers.
Okay. So date on the right, index on the left. And that left part, the index, that's the key.
That's the key to everything, because you don't have to stick with 0, 1, 2, 3.
Right. This brings us back to the power of the index. You said position-based, like a list, or label-based, where we can set our own custom labels.
Exactly. And that's the big conceptual jump. When you assign your own custom labels, maybe city names or product IDs or dates, the series starts to act a lot like a fixed-size dictionary.
A dictionary!
How so? Because those custom labels you assigned become the keys to access the values. You're not using the position anymore. You're using the label you gave it.
Okay, can you give an example? The source mentioned one with characters.
Yeah, so imagine you have a series with some characters, A, B, C, etc. But instead of the default 0, 1, 2 index, you explicitly give it numerical labels like 10, 11, 12, maybe to 22.
Okay, so the labels themselves are numbers, but not starting from 0.
Right. They're custom IDs. Now, if you want the character O, and maybe it happens to correspond to the label 16 in your custom index,
Yeah.
you'd ask for the element at label 16.
And it gives you O, regardless of whether O is the 5th or 10th or whatever item in the actual sequence.
Precisely. The label 16 acts like the dictionary key. You're looking up by label, not by position.
Got it. That shift from position to label is huge, and probably where a lot of confusion starts.
It is.
Which means we need to talk about how you pull data out, subset selection, because this is where that position versus label distinction really matters.
This is where it's really tactical in data analysis.
Yeah.
And the core confusion, the thing that catches everyone, it's knowing when to use the label, that explicit key, versus when to use the position, its physical spot in the line.
And this brings us to the famous, or maybe infamous, .lock versus .ilock showdown.
The classic. Yeah, everyone stumbles here initially.
So let's break it down. Start with .lock. What's the rule?
Okay, think L for label, .lock, selects data purely based on the explicit index label.
So if my labels are NYC, LA, Chicago, I use .lock NYC.
Exactly. You're calling it by its name, its label. Doesn't matter if NYC is the first or fifth item. .lock finds the label.
Like finding someone by their name tag, not their seat number.
Perfect analogy. And here's a really critical difference, especially when you're selecting a range of data called slicing. With .lock, the start and end labels are inclusive.
Inclusive, meaning?
Meaning, if you have labels, say, numbers 3 through 10, and you ask for data .lock 3, 4, 5, 6, you get the data associated with labels 3, 4, 5, and 6. It includes that endpoint label, 6.
Okay, .lock selects label, and slicing includes the end label. Got it. Now contrast that with .ilock.
Right. Think under integer position. .ilock selects data based purely on its position in the series, starting from 0. It completely ignores any custom labels you might have set.
So this is like finding someone by their seat number, your seat, first seat, second seat.
Exactly. It only cares about the order, the integer location, 0, 1, 2, 3.
And the slicing behavior, you said it's different.
It follows the standard Python way. When you slice with .ilock, it goes from the start position up to, but excluding, the end position.
The standard Python off by one feeling.
Precisely.
Yeah.
So data.ilock 3.6 gets you the elements at positions 3, 4, and 5. It stops before position 6.
Okay, .ilock integer position, and slicing excludes the end position.
You got it.
But wait, what if, like in your earlier example, my labels are also integers, like 10 through 22? If I ask for data 16, how does Pandas know position 16 or label 16? Using .lock and .ilock seems essential there.
Exactly. That's why they created two distinct methods. If your index labels aren't the default 0, 1, 2 integers, or if they're strings, .lock 16 will always look for the label 16, and .log 16 will always look for the item at the 17th position 16, since it's 0 indexed.
So using .lock and .ilock makes your code unambiguous. You're explicitly stating, I want the label, or I want the position.
Precisely. It removes the ambiguity, which is critical for writing clear, maintainable, and correct code, especially when your data might get sorted or filtered later on. Choosing between them is fundamental.
Okay, that clarity makes a lot of sense. So now we know how to create a series and how to precisely select the data we want using labels or positions. Let's shift gears. Section 3. What can we do with the data once we have it? Manipulation.
Right. So beyond just holding data, series are built for calculations, standard math operations, addition, subtraction, multiplication, division. And Pandas gives you dedicated functions for these, like .add, submul, .div, more explicit than just using plus bus.
And what's really interesting, according to the source, is how it does these when you combine two different series. It's not just pairing up the first item with the first item, is it?
No, and this is maybe the most important concept in Pandas operations. Index alignment.
Index alignment, okay.
When you add, subtract, or do any binary operation between two series, Pandas first looks at the index labels of both series. It only performs the operation between elements that share the same label.
So hang on. If I have Series 1 with labels A, B, C, and Series 2 with label C, A, maybe in a different order, when I add them, Pandas doesn't just add the first elements. It finds the A in both series, adds those values, finds the B in both, adds them, finds C in both, adds them, regardless of their position.
Exactly right. It matches based on the label, not the position. This is a huge built-in safety feature.
How is it a safety feature?
Well, imagine your two series cover slightly different sets of things. Maybe one has data for A, B, C, and the other has A, D, D. What happens when you add them?
I guess A and B get added. What about C and D?
Pandas calculates the sum for A and B because they match. For C, only in the first series, and D, only in the second. There's no matching label in the other series. So the result for C and D will be nan, not a number.
So it doesn't just crash or, worse, add C from the first series to D from the second because they happen to be in the third position.
Correct. It prevents misalignment errors. It automatically handles missing data or mismatched data sets by using nan rather than giving you a garbage result. That alignment based on labels is why Pandas is so reliable for data cleaning and analysis.
That sounds incredibly useful compared to trying to do math on raw Python lists where you'd have to manually check everything aligns.
Oh, it's night and day. It ensures structural integrity. And beyond basic arithmetic, series have a whole suite of built-in analytical methods.
The source listed quite a few. Some meme prod. Why is having these as methods on the series object itself so much better?
Speed and convenience, mainly. Remember, Panda series are built on top of NumPy arrays deep down.
Right.
So these operations like sum, mean, calculated the product, prod, even statistical things like covariance, cov. Yeah. Between two series, they're highly optimized. They run very, very fast because it's vectorized computation.
Meaning it avoids slow Python loops.
Exactly. Instead of you writing a for loop to add up all the elements, you just type myseries.sum or myseries.mean. It's clean, readable, and much faster, especially on large data sets.
Okay, fast and convenient calculations made safe by index alignment. Makes sense. One last piece on manipulation. Data consistency. Data rarely arrives perfectly formatted, right?
Almost never. So conversion operations are vital. This is about making sure the data inside the series is the right type for what you need to do.
And the main tool for that is .astype.
Yeah, .astype is your friend here, along with maybe .tallist if you need to convert it back to a standard Python list for some reason. But astype is key.
Give us a typical scenario where .astype is essential.
Okay, classic example. You load data from a file, maybe a CSV. There's a column for price. Should be numbers, right? But maybe some values were entered with a $sign or commas, or maybe it was accidentally saved as text.
So Pandas reads it in as strings, not numbers.
Exactly. It sees 1099 or 1,000 and treats it as text, an object type in Pandas terms. Now, you can't calculate the average price or the total sales if your price column is full of strings.
Right, math on text doesn't work.
So you'd first clean up the strings, remove five, and then use series price.astype float to convert that column of text numbers into actual floating point numbers that you can do math on.
It's a data cleaning step to enable analysis.
Fundamentally, it ensures your data type is consistent and correct, so those index-aligned operations we talked about work properly. You need numbers to do number things. Ask to make sure you have numbers.
Got it. Okay, let's try and wrap this up for the listener. Quick summary.
Let's do it.
We've established the series is that core one-dimensional labeled array in Pandas. Think single spreadsheet column.
Yep.
We saw its power comes from that dual indexing, access by integer position like a list, or by custom labels like a dictionary.
Critical distinction.
Which led us to the .lock versus .ilock difference. .lock for labels, inclusive slicing. .ilock for integer position, exclusive slicing. Getting that right is non-negotiable.
Absolutely key. Nail that down.
And finally, we saw how Pandas makes calculations both easy and safe through methods like .add or .mean, and crucially through index alignment, matching labels before doing math, plus .astype for data type hygiene.
Connect that to the bigger picture. The series really is the atom. Everything else, especially the data frame, is built from these. Mastering how to access series data using both labels and positions, really understanding that index label is like a fixed key. That's the bedrock skill for efficient Pandas use.
It sets you up for everything else.
Totally. You build efficiency from the ground up by understanding the series first.
All right, so for that final provocative thought, something for you to mull over, we've spent this whole time on the series, the single dimension, the single column.
Right.
But we know Pandas is famous for the data frame, the two-dimensional table, rows and columns.
Yeah, the workhorse.
So if the series already forces us to be so careful about distinguishing position versus label in just one dimension, what kind of indexing complexity does the data frame need to handle?
Think about it. You now have two dimensions. You need to select rows, potentially by position or R by label, and you need to select columns, also potentially by position or by label, the column name. How does Pandas provide a clear way to say, I want the row with label X and the column at position 3, or rows from position 5 to 10, but only columns named price and quantity? The complexity of managing label and position across two dimensions, well, it doesn't just double, does it?
It sounds like it multiplies significantly. That's definitely something to think about.
Food for thought as you move from the series to the data frame.
Fantastic. A great place to leave it. Thanks for joining us on this deep dive into the Pandas series. We'll catch you next time.